Okay, hello everyone. Let's go over this past exam together. So the first thing we do is to write down our name, and don't forget to circle the section that you're in. For example, if I'm in Maria's section. Okay, let's get started. So first of all, if you have function of two variables, x and y, and so you have to find the gradient of f at this point at 2, 1. We can easily do this by direct computation. So the definition of gradient is you compute the directional derivative fx and fy, and which is 2xy squared minus 1 and 2x squared y. Okay, and then if you plug in the point 2, 1, we get 2 times 2 times 1 squared minus 1, 2 squared times 1. So in total, the vector you get is 3, 8. And the next question, so where the question is slightly different. We have to find the directional derivative along this direction. But since this is not of unit length, we have to normalize it first. Plus j hat. So the normalized vector is minus 1 over square root of 2 and 1 of square root of 2. And the directional derivative of f is exactly the dot product of u with gradient f. And we've computed gradient f previous, like in A. So the answer is, put gradient f here, then we get, this is, denominator is square root of 2, and the numerator is 5. Okay. And what about part C? Write down the equation for the tangent plane to the graph of f at this point. So the first thing we have to do is to understand what is the graph of f. So graph of f is a level set x squared. So f is x squared y squared minus x. Square y square minus x minus z equals 0, right? Because this is equivalent to saying that z equals x squared y squared minus x, where the right hand side is exactly f of fxy. So, and we have to find the tangent plane to this graph. And the tangent plane can be calculated by knowing the derivative, by knowing the gradient of this function. So we didn't do anything right now. We just copy the function from this equation. So gradient g is 2xy squared minus 1, 2x squared y minus 1. This is the normal to the graph, to the tangent plane, to the graph of f, to the tangent plane, to the tangent plane. Okay. So, and we have to plug in this point. 2, 1, 2, which, so we just skip the computation. We get 3 at 8 minus 1. So from now on, we can write the tangent plane as this. The tangent plane is 3x plus 8y minus z equals some constant d. To determine this d, we can do by plugging in 2, 1, 2. We get d as 3 times 2 plus 8 times 1 minus 2, which is 12. Okay, so we have to understand like every concept mentioned here. So the graph of f, we know is this z equals fxy here, and this can be understood as the level set when your value is 0. So maybe the level set of gx y z equals 0. And to find the tangent plane, we can compute the normal of this tangent plane, and the normal is parallel with gradient of g. So after computing this gradient of g, we can compute the tangent plane is of the form like this, but there's also one missing constant that we don't know yet by just knowing the normal to the tangent plane. So the final thing we do is to plug in a point on the graph of f. Then we know that d equals 12 here. Okay, let's see how about the second question. Okay, so you have a function of 2 variables, and in part A, they have already told you the critical points are at these 2 points, so you have to find them. But you do have to classify them into like local maximum or local minimums or saddle points. So from here we know gradient at 0 is this 0 vector, and also gradient at -1, -1 is also a 0 vector. And so to classify them into, say, local maximum or minimum or saddles, the thing we have to do is to find their Hessians. So the Hessian is this matrix given by the second derivatives of f. So we compute fx is 3x squared plus 3y, and fxx is 6x, while fxy is 3. Fy is equals 3y squared plus 3x. Fy equals 6y. Fyx equals 3. So we know the Hessian matrix equals 6x 3 3 6y, and at 0 0 the matrix looks like this. Then we compute its determinant, which is 0 times 0 minus 3 times 3. So this equals minus 9. Because this is negative, it tells you that 0 0 is a saddle. What about at the point minus 1 minus 1? Then you get the Hessian is this matrix, and if you compute its determinant, you get minus 6 squared minus 3 squared. So in total you get 27, which is positive. So it could be a local maximum or a local minimum. But we do know the second derivative of fxx at this point is minus 6, which is negative. So near this point, it goes down when you cross this point. Then you get at minus 1 is a local maximum. Good. Okay, how about part B? So based on your answer in part A, mark the correct contour diagram of F below. So, okay, so from what we know up here, I would say the condition here is easier to identify on the graph, because if this minus 1 is a local maximum, then you would have a like maybe a concentric circle like here, or it's not quite concentric circles, but if you draw this like more with more details, then maybe we'll see a concentric circle. But anyways, from this information we see it's either this diagram or this diagram. And there's a saddle at the origin. So, okay, so if x at 0 is 0, because it's a saddle, right? In particular, it's a critical point. But at this fourth diagram, it doesn't appear to be a critical point. While for this one, it does look like it's a critical point. And with your, of course, fx equals 0 and fy equals 0. So the answer is this third one. Okay. Let's move on to 3. So, okay, you have a dog right here chasing a rabbit. So a rabbit around this mountain. Okay, so let's don't make this graph too complicated. You chase the rabbit over the mountain, and then shadow of the path is to the xy plane is given by the curve right here, and the elevation of the mountain is given by this function. So find the highest and lowest elevation. Okay. So let's try to formulate this problem into something more doable. So the question asks, maximize or minimize z equals fxy under the restriction of 4 equals 4x squared plus y squared, which we can let this be g. So if we formulate this in this terminology, we can see we could utilize Lagrange multiplier for this problem, like maximize or minimize a certain function under a restriction like this, like g equals some constant. So Lagrange multiplier tells you, first you have to compute the gradient of f, which is minus 8x minus 3y squared, and minus g. The gradient of g is 8x 2y. So we have to solve this equation. Gradient g equals lambda of gradient g together with 4 equals g. And to put this into more concrete terms, we have concrete equations. We have minus 8x equals 8 lambda 8x to lambda y, or equals 4x squared plus y squared. Oops. So if x equals 0, then then we don't know about lambda, but we can deduce from the last equation, the value of y, then y equals either positive or negative 2. However, if x doesn't equal to 0, then from this first equation, we know lambda equals -1. And we can utilize the second equation to see that this equation holds. Then we can solve so either y equals 0 or y equals 2/3. So if y equals 0, then x equals, so maybe we can do this more slowly. Then 4 equals 4 squared plus y squared, which is the equation right here. Then x is either positive or -1. Then the next case, we also compute by the third equation. We get x is either positive or -2/√3. So now we have different candidates of possible local maximum or minimum, and it's global under the restriction because, as we can see, the restriction right here is a bounded closed subset of the xy plane. So the maximum or minimum must be attained. Then we can find them through Lagrange multiplier. So let's skip the detailed computation. But after testing every point, we find the maximum of f is 18, which is at 0 minus 2, and minimum of f equals 2 and at 0, 2. All right. Let's look at problem number 4. So we have to find the volume enclosed by the surfaces, these two, and between the planes right here. Okay, so let's draw a very naive picture of this. So we can think of this as you have some region on the xy plane, which sort of looks like this. And then for the surface, it's some sort of paraboloid facing downward. So it's like this sort of, and you have, so it's the same paraboloid. So sort of like this. Okay. And you have another plan. Z equals minus 2y. So it cuts the paraboloid maybe. So imagine there is a plan. I should use another color. Like this. Okay, this is not very accurate, but I was just trying to say that we're integrating over a region on the xy plane, and then our integrand is the height of this first surface of the paraboloid minus the height of this lower surface, which is exactly a plan right here. Okay, I don't think this plan is accurate, but this can be served as our intuition to simplify this problem using double integral. So what we do is we can first identify the region on the xy plane. So you have x equals 0 and y equals 1. Also x equals y. So this region. Now we have on the integral side, this is, we can first integrate over dy, then dx. So for y, it goes from x, from here, from this line, to y equals 1. So x to 1. While x goes from 0 to up to this place, 1, 1. So x goes from 0 to 1. Okay, and then we put our integrand right here. So this integrand should be the height of this paraboloid minus that plan, minus the height of that plan. Okay, I don't believe we have enough space to write down the integrand, so let's squeeze a bit. So the integrand is 2 minus x squared minus 3y squared minus 2y. Okay, so it all boils down to this double integral. 2 minus x squared equals from 0 to 1, 2 minus x squared multiplied by 1 minus x. Because right here it's for y it's just a constant term, so I just multiply by the 1 minus x, then I get this term right here. And for the rest, we do the usual integration. Then in the end, by direct computation, we're ending up with this integral. And if you really compute this, the answer equals 5/6. Okay. So I would say the hard part for this question is how do you convert this problem into computing a double integral. So you first fix the region that you're integrating over, so the region on your xy plane, and then determine like which surface is higher. So for this case is this paraboloid, and then you take the height of this one minus the height of the other one, and then you integrate over this height, integrate this height of the region. So this is the computation we just did. Okay, for the next question. Okay, you have a 3D curve C parametrized by this vector for t between minus pi to pi. And find the mass of a wire in the shape of C if we have the density function right here. So in order to compute the mass, what we do is compute a scalar line integral, right? So we're integrating over this curve C, so write down the C here, and the density function rho ds. So we're doing a scalar line integral, which by definition is we're integrating over from minus pi to pi of, plug in the RT into the density function, and R prime T dt. So don't forget the absolute value for this scalar line integral. Then we can do by direct computation. This is 2 cosine t plus 10, and R prime t is minus 2 sine t, 2 cosine t, 1. So its length, its magnitude should be, so you have 2 squared sine squared t, because of the squared, the negative sign goes away, and cosine squared t plus 1 square, and take square root. Then because cosine t and cosine squared t plus sine squared t equals 1, then you get 4 plus 1 square root, so square root of 5. Okay, dt, and we can pull out this square root of 5 because it doesn't depend on t. It's just a scalar multiple. And let's compute this integral directly. Okay, so sine pi equals 0 and sine minus pi also equals 0. Sorry. And pi squared over 2 minus negative pi squared over 2. So this also equals 0. Plus 10 pi minus 10 minus pi. Okay, so overall we get 20 square root of 5 times pi. So this is the mass we get by computing this scalar line integral. Okay, next. For 6, a particle moves along the path of this RT. Doesn't look so nice, I would say. For t goes from 2 to 4. If the particle is subject to a force field, F, we have to find the total amount of work done by F on this particle. So this is a classic question for vector line integral. And if we see a problem like this, the first thing we want to do is perhaps to find the curl of f. The curl of f is qx minus py, which is ex cosine y minus ex. Differentiate sine y, we get cosine y. So this is 0. So f is curl free. Then if we can find the potential of f, we can utilize fundamental theorem of line integral to compute the vector line integral of f directly, right? So a potential of f, we can choose. If you're familiar with like integration or differentiation, then you can probably see, not within a minute, that this is a potential of our vector field f. So ex, e to the x sine y. You can check by directly plug in fx, fy, this is f. Or you could integrate f, then get this potential. Okay. So fundamental theorem of line integral says that if we're computing this vector line integral, then it equals to computing. So it's more like fundamental theorem of calculus because we have a potential. So we plug in our endpoint and our starting point into a potential little f, and we get, so R4 equals log of 4 plus 1, so natural log 5, and pi. And, well, R2 equals natural log of 3 pi over 2. So we plug in psi pi minus e natural log of 3 psi pi over 2. So we get 5 psi pi, which is, so psi pi is 0, we don't look at this term, it's 0, 3, and for psi pi over 2, it equals 1, right? Therefore, the answer is minus 3. Okay. For this problem, if you do like direct computation, I would guess it would be complicated. But if we can notice that f is curl free, then, and by this direct computation we can see easily this vector field f is curl free, then we can find the potential of f, one potential of f, by maybe integrating over f, or you could see directly, if you're more experienced, directly that this is one potential for vector field f. Then we can utilize fundamental theorem of line integers, and we could simplify our computation into just computing this, like you plug in the points and then compute the function. Okay, so this is for number 6. Okay, for number 8, I think things are getting more complicated here. Now we are given a slightly more complicated curve like this, and we're computing a vector line integral over this curve, and this vector field doesn't look nice, so we would try everything to avoid direct computation. But this needs a little creativity, so we could complete this curve by adding one more c prime. And if we're looking at c0, which equals c plus c prime, this is a closed and positively oriented curve for the inside quarter circle D. So if we are looking at the vector line to go over this closed circle, we can do direct computation like this. Qx. So if this is f equals pq, then we put the curl n. Okay, this is one way we could approach this problem. But before we do this, let's check if our curl is nice enough for us to carry out this computation easily. Because if it doesn't simplify this problem, then we would also have to, but we also have to compute another line growth for the curve C prime. Then in total, this way may not be easier. So let's compute qx minus py, the curl, which is y e to x plus 1 minus 2y over 2 e to the x plus, okay, no, plus 0. And so in total we get 1. So this area integral gives you the area of D, which is a quarter circle, a quarter disk, because for D is 2-dimensional, right? So it's a quarter of the whole area of a full disk. Then we get pi. So in order to compute C, the vector line integral over C, we could compute the whole closed curve minus C prime, right? And for the first one, we know it's pi. Then we have to compute the vector line integral on C prime. So for C prime, you could choose a parameterization 0, because we're on the y-axis, there's no x influence, 2 minus t for t between 0 and 2. Okay, then C prime f dr equals, where t goes from 0 to 2, and we plug in that f for this t. So f is right here. I'm plugging 0, 2 minus t to this vector field f. 2 minus t squared over 2 t 0 minus 1 dt. So we get this integral, and the answer as minus 2. So, okay, because we have computed this, we just plug in into the original equation. We get pi minus -2, which is pi plus 2. So this is the answer for problem number 7. Okay, we see this vector line integral, which is not so nice to compute directly. It looks kind of terrifying, so we use another way to avoid the direct computation over the circle, maybe a quarter of the circle, and then quarter of the circle and this line segment. We can add the C prime to complete the curve into a closed curve, C0, so that's positively oriented for the disk D. Then the computation is a lot easier because the curl is simple and the vector line integral is simple for C prime, right? Because if x is 0, we don't get the annoying term of this sine x squared or this x. We don't even have that e to the power of x because it equals 1 when x equals 0. Alright, so for a complicated vector line integral, we can use, I guess I forgot to mention, this is Green's theorem. For a complicated vector line integral, we could sometimes use Green's theorem to avoid some line integrals that we don't really compute by converting the problem into an area integral, and maybe a simpler vector line integral like the one here. Okay, so let's move on. Okay, problem number 8. For each part below, write down a vector field. So write down a vector field such that it satisfies some conditions. You don't have to make your own justifications. But if you do provide your justification, then there might be some partial credits. Okay. So for number 8, for number 8, part A, we have all vectors are of unique length and are perpendicular to the position vector at each point. So position vector is xy, right? Then one choice, or if we have to be perpendicular to the position vector, then we could choose some stuff that is parallel to minus yx, right? Because the dot product of xy with y minus yx is minus xy plus xy, which is 0. But every vector has to be of unique length, so we can choose fxy is minus yx over minus y squared plus x squared. So this is a vector of unique length because we've divided the vector by its the vector right here by its length. Okay, for part B, all vectors are parallel to the x-axis, and the vectors along each vertical line have the same magnitude. This is part B. Okay, parallel to x-axis. So fxy is parallel to 1, 0. Right? So, x 1, 0. Yeah, like this. And vectors along each vertical line have the same magnitude. Okay, I guess we could just choose a constant vector field, which is 1, 0. So that is of the same length, same magnitude at each point, not just along each vertical line. And every vector is parallel to x-axis. Good. Now let's look at number 9. Match each double integral on the left to the equivalent expression on the right. Okay, as previously, you can justify your answer or not, but I would recommend to justify your answer. So for part A, for capital A, okay, we don't really have a space here, so let's zoom in a bit. So for number A, x is from -1 to 1, and y is from length of x to square root of 2 minus x squared. So this graph looks like, okay, we have x equals -1 here, and x equals 1 there. So this is the bounds for the first condition. And for the second bounds, for the second pair of bounds, we have y equals x right here. So this equals y equals the absolute value of x for this first quadrant. But for the second quadrant, it should be y equals -x. So it's not an entire line. It's more like 2 half lines for this y equals x, as absolute value of x. And for the other bound, it's a half circle because this equals that to that, then we're in a circle, right? X squared plus y squared equals 2. So this is a circle, a half circle, upper half circle here. And they exactly intersect on these 2 points. Well, so okay, maybe another color. So 1, 1, and that point is minus 1, 1. Then the region we're looking at is exactly this quarter disk, as you can see. So this integral equals to, if we write everything in polar coordinates, then we have to determine r is from 0, right, to square root of 2, because the equation right here, this indicates the radius for the circle is square root of 2. And the bounds for theta is from here to right here. So from pi over 4 to 3 pi over 4. And the answer should be number 4. So this is the answer. Okay, so this is for part A, capital A. Okay, let's adjust this a bit. Sorry. Okay, good now. What about part B? So, let's also look at the region we're integrating over. So x is from minus 1 to 1, and y is from 0 to absolute value of x. So x equals minus 1, x equals 1, and y equals y from 0 to the curve, the 2 half lines. So here, we're integrating over here. Thus, if we interchange the order of integration, then we get, let's start with dx. So for x, it goes from minus 1 to minus y, right? So this is y equals minus x. So minus 1 to minus y. And y goes from 0 to 1. This doesn't look clear at all. From 0 to 1. So y from 0 to 1. And for the other part, okay, we don't have space. For the other part, y also goes from 0 to 1, while x from y to 1. So the equivalent expression for this integral is number 2, right? Because this part matches this part of the integral, and that part matches that part. Okay, so the answer is number 2. Okay, we're again running out of the space for the computation for the next one, so let's adjust a bit. Okay, I hope this doesn't look confusing. Well, it does look confusing. Okay, forget about it. For number C, we just do something similar. So if x, maybe I should draw the graph on the left. So y goes from 0 to 1, and x goes from minus y to y. So x equals, so we have these two lines, so from minus y to y. So this is the region we're integrating over with. And so, okay, so we can change the order of integration because this doesn't really look like a polar integral, right? I would guess the answer is number 1, but let's check as well. So by changing the order dy dx, so y goes from, let's first look at the left side of this. Y goes from y equals minus x to y equals 1, minus x to 1, and this is the left part, so x goes from minus 1 to 0, minus 1 to 0. And for the left part, dy dx, y goes from y equals x to y equals 1, x to 1. And now x varies from 0 to 1, right? Here. Okay, so this integral matches with this, and this part also matches with the second part. So the equivalent expression for number C is number 1. Okay, this part looks messy, but let's put our answer. here. So A matches with number 4 and B matches with number 2. C matches with number 1. Okay, so there's one interval left just to mess you up, I guess. Okay. So we're nearing the end of this exam. Our final problem is this true or false question. You don't have to make your justification, but again, I would encourage you, if you have time and you have checked other problems previously, then you could try to write down your justification, so that you might still get some points if you don't really get the answer correctly. So for this final problem, let's just get started. For part A, can we pull out this integral of y and ignore it and don't integrate over x for this part? No, because h2 of x and h1 of x, they're both depend on the x. So you can't just pull out something that depends on x out of an integral with respect to x, right? Okay, so false. And part B. Again, we have a function. Does it attain a global maximum on this set? So let's look at this set. If it's closed and bounded, then we know it must obtain a global maximum on this set. So x equals 0 and x equals 1. Okay, perhaps we have to draw this closer. And y is less than 2, so y equals 2, and maybe y equals minus 2. So we're in this region, which is clearly closed and bounded, so it obtained a global maximum. Okay, good. Now part C. If all the directional derivatives for f is 0, then f has a critical point at AB. So critical point at AB means this vector on this gradient is 0, right? So we have to check this. But du hat f a b equals the dot product of u with respect to gradient f, right? And this is always 0, so we could choose u hat equals 1, 0 or 0, 1. Then this will gives us that So 1 0 dot gradient f, this is fx, and this equals 0, and similarly gradient f, this is 0, right? And the right hand side is fy. So yes, the gradient at AB is 0. Thus, f has a critical point at AB if all the directional derivatives for f equals 0. So the answer is true. Okay. The curve for D, the curve is shown below. So it doesn't specify where the theta lies, but we can see directly, at least it has to lies from 0 to pi in order for this expression to make sense, right? Because the radius is always non-negative. So the area of the region inside this curve is given by the polar integral. But now we sense something not so rational here, because theta exceed the reasonable region for theta. It goes to 2 pi. So theta could be, so r could be negative. It doesn't really make sense. Therefore, the answer for part D is false. And if you want to be more precise, this integral equals, the only thing you have to modify is the 2 pi here, and then so the area should be this integral instead. Okay. Part E. So you have a continuous vector field F and the parameterization of a curve so that this dot product is greater than 1 for all t. Then does it necessarily imply that the whole vector line integral is greater than 1? I'm afraid the answer is false, because if we write down the definition, so say t is ranges from A to B, then suppose this equals, say, 2, which is greater than 1 for all t, but your A equals 0 and B equals 1 over 3. So let's suppose we're in a case which satisfies all the conditions here, but then you get this integral, which is 2 over 3, and it is less than 1. So the answer is false. And you can easily, for example, find a line segment which realize in a continuous vector field which realize this set of conditions and make a legit counterexample, but the intuition for this problem is, okay, even though you have your dot product here is greater than 1, but if this is not large enough, it's just slightly larger than 1, and your curve is not somewhat long enough, then no, your total vector line integral can't be greater than 1. Yes. Okay, so let's do the final problem for this entire exam. Good. Okay, let's move this a little bit. Okay. Good. So let's see, be a unit circle, traversed once. It's important, only traversed once. If it's twice or 3 times, then the answer for this vector line integral might be different. Okay, so traversed only once and counterclockwise. So let's draw the picture for our unit circle. And we have a perfect parameterization for this unit circle, which is cosine t, sine t, and your t goes from 0 to 2 pi. Okay. And this x dy integrate over c is the shorthand notation for the vector line integral pq for the vector line integral, say p dx plus q dy c equals pq. So this is our vector dot dr. Okay, then we expand this by plugging our parameterization. Then we get and our explicit vector field f. So this is 0 cosine t dot minus sine t cosine t dt. Okay, so and t is from 0 to 2 pi, right? And the answer is for this integral is pi, because don't forget, because sine and cosine, they're only differ by a translation. So if you integrate, and we take the squared here, so that if you integrate over the whole 2 pi, because they are periodic, and then they differ only by a translation, then the integral of their squared must be the same. And this is pi integrate over 1, which is 2 pi, right? So if we're only integrating cosine squared over over 0 from 0 to 2 pi, then the answer is half of the 2 pi, which is pi. So the answer for F is true. Okay, so that's the past exam 2 for fall 2024. And good luck to your exam 2. Thank you.